I need to do, if I want to make this union, then either I have to make all these names, that means all these names to UJ, or I have the option of making all these names to UK. That means either A, the name of A remains, or the name of B remains. And the other is actually converted into the other's name, component's name is converted into the new component. Okay? So there is two possibilities. So what is normally done is normally the size of the bigger component or the name of the bigger component is kept. Okay, so suppose this is the case that the cardinality of A is less than the cardinality of B, then I will keep the name of B, and what I will do, I will change the name of A. That means for all the elements of A, I will change the elements here. Let's say A is here, A is this region, and B is this region, let's say. So what I will change the name of A into this. So I will make it like this. Okay. So actually in coding terms, you can see pseudocode terms, you can say that something like this. This is pseudocode. For all X in A, you will write component of X is equal to component of B. Here I write component of not B. Let's say Z. Z is an element of B. What do? You take any element Z of B, and for that you take the name of Z, and that you assign to every element X of A. Because Z is any element of B, every element of B has the same name. Okay, so that name I assign it here. Okay, so I change it for all A. The reverse will follow. I mean, if the component A has a bigger size, then just the reverse will follow. Okay. If both the components are of same size, you can do anything basically. You can do anything. Anyone you can do. That does not mean. So this is how you do. See, you understand. What you do, you actually change the array. You actually change the array. You change the names. So now this is the general approach how you do for implementation of find and union for an array. Now let us take the time that is required for each of these operations. So make union find, how much time it takes. If you see that for you have to make this thing for every element in the vertex set. So this will take order of n time because there are n vertices. Okay, you need to initialize the entire array, so it needs order of n time. What is the find operation? Find component V. So it just returns the name, content of one array element, and that array element is accessed by its index. So remember, this V actually means some sort of real index. So this find operations require constant time, order one time. Okay, because array accessing is very efficient. You know the index, you know the content of that position immediately. Now here, so this is my make union find. This is my constant time of find, but how much time it takes for the union? Okay, so here, if you look at the union, it depends on what is passed here as A and B. And in the worst case, actually A and B can be proportional to actually order of n. Okay, size of A and B, because you can think of when it can happen. So let's say half of the array, I have roughly half of this array, I have named as say U1, and the rest half of the array I have named as, let's say, UN, the last index, and then I want to make a new component out of this. Okay, so potentially A can be order of n, and B can be order of n size. Okay, so see, n by 2 and n by 2, this actually does not change the order. So order wise, they are actually order of n. So that's what the meaning. So A can be of size order of n, B can also be of size order of n. And then when you do this thing, depending on whether A strictly less than B, or uh, the cardinality of A is strictly less than B, higher than B, actually for one of them you have to change the name. So what convention we follow? Keep the name of the bigger size. Okay, keep the name of bigger size. What does it help? It helps me to change the name of smaller size. That means I have to make as few changes as possible. Okay, so but in the worst case scenario, this A, the smaller size, uh, whose name I need to change, that can be actually of order of n. So I may have to change the of this array. Okay, this union operation actually, in the worst case, will lead to order of n time, one union operation. Okay, so what is the thing that we got in this array implementation of the union find? Component creation, that is make union find to initialize this data structure, that requires order of n time. Okay, the find operation is quite fast. This is constant time, much better than even log n. Whereas this union operation is the limiting thing. It is order of n. Remember, most of the implementation, the make union find anyway will take order of n. So it does not actually matter too much. You see, what is the expectation? The find is quite fast, union is fast. But anyway, you need to initialize the data structure, and that time you will require order of n. That's not a limiting, because you will initialize the data structure. You will actually make many calls to this find and union operations. Just a minute. So I hope this is clear to all of you. If you have any questions, you can. Better implementation of this union find data structure. So union find using link. So I hope that everybody knows what is a linked list data structure. Okay, if somebody does not know, then I will request him to linked list data structure. Okay. So what I do here is, again, I mean, I have to make union find. Okay. So let me first introduce you how we make this. So in this case, for every vertex, I make one box kind of thing, and where I have this vertex value, and I have a link actually that is actually set to null. So for every vertex, let's say u1 blah 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 to un, I create one linked list, individual list basically. I create one individual list. Okay. And this is my make union find. Okay. This is what I do inside this make union. So I'm not going into the actual pseudocode, but I'm just telling how to do that. So basically, I need to create a box like this. So you know how to do it, like malloc, and then put the two component values. Okay. So you can do this, and remember they are not linked. Each vertex is a single list of only one element, with the value part is the node or the ID of the node, and the next part is actually grounded or is set to null. Okay, so each is an individual list, so they're disjoint and all the n individual lists are there. So now what I do is, I mean, uh, so what is there is I somehow I somehow so find, I have to do the find, right? So if normally I do find, what I do, I return, I mean, at this point of time, if you see that its next is actually null, right? So if I ask, I check whether the next is null. If the next is null, then I return the content of the value in this box, and that is the name of the component. Okay. So I do like this. Later I will see how the find is not just that. Find is more important here. Now I give just a simple example. So initially, suppose I have two such vertices. Okay? Let's say one is u2, another is u1, and this is the link. This is the link. Okay. Now suppose I want to make union of these two. Union of these two. One set I pass u1, and the set I pass u2. This thing I want. So what I can do now is that I can just change this pointer, and I can make it point to here. Okay, I can just change the pointer. So what does this do? This means this node is pointed to u2, and the name of this that means this is some sort of, u2 is some sort of a higher node, or you can think of this as a parent node, and this u1 is a child node, and the name of the parent actually prevails. Okay, so later when I will ask, okay, what is the name of u2, I will say, okay, what is the next of u2? Next of u2 is null. So okay, so return u2. What is u1? Okay, what is the find of u1? What is next? Next is not null, it is pointing to somebody else. Okay, let me go there. And there, is it pointing to somebody else? It is pointing to null, so I will return u. Right? So both the names are u2. Right? Now let us look at a bigger component. I mean, like this. I mean, this is essentially tree structure. So you can think of one component like this. Okay, I say u1, and this another component is u2. Let's say something like this, and this let's say this is pointing to this. Okay. Now this is the situation. Now suppose I ask union of two sets A comma B, where A is equal to U1 comma U2, B is equal to X1 comma X2. Okay. So what I do is I just union operation. What I do, see, whenever I pass this A and B, so basically in as an additional thing, you can think of how do I pass these two sets inside. I somehow have to do it. So what I will do, I will just pass the pointer to the root, actually pass a pointer to the root. Okay. I will not pass these sets just as like this. I will not maintain. I will pass this pointer as pointer of A and pointer of B. So what I will do inside the union, I will just make this emptiness, I will remove. Okay. And I will make this point to this. Then it will become a new component rooted at X. That means everybody's name is automatically changed to X. So effectively, you can think of that union operation takes a constant amount of time in this case. Okay, because you just need to change the name of the root. You just need to change the pointer of one tree and make it point to the root of the other tree. You want to just do that. Now, again, likewise, like earlier, actually, I'm trying to explain this with a picture. Please try to understand this. Uh, it may so happen that this one is a very big tree, okay, and this one is a tree like this, okay. So now this is one component, and I pass you this is A, this is the B, okay. Then when I pass this union and A and comma B, then there are two possibilities again, right? One is I make this point to this. This is one possibility, or the other possibility, I make this point to this. Okay, these are the two possibilities. So likewise, what I do is I keep the name of the old component, okay, or the bigger sorry, I keep the name of the bigger component. So that means I will do like this. I will change the name of the smaller component. So I will ask the smaller component to point to the root of the bigger component. Okay, that's what I will do. What? Why I am doing this? It will help in some sense. I will explain later. Okay. In see here in this particular case, since I am just changing a pointer, the I mean the it doesn't actually make much difference. I mean, at this point, I mean, in terms of how much you change. In both the cases, you just need to change one pointer, okay, and both will take actually constant amount of time. So, I mean, both are equally efficient. So, why I am making the smaller component change the name and not the bigger component, that will be clear when we try to analyze the time. So I hope the union operation is clear here. And the find operation, how do I make the find operation? So find operation, let's say in this general case, what I do here, find operation is not so simple. Let's say, see, after this joining, what this tree look, this is some sort of, which say you should think this is a some sort of uh, I mean a very big tree. So you can think of it is something like this. So this node has 3 children, and this has again 2, these are again 2. So it's something like equivalent like this. This has something, now this has this. It is like this. Okay. So after the union, it is like this. So now suppose these are two nodes A and B. Okay. So suppose I ask this operation. I ask find of A. How I should do? So what I should do? I know I check whether finds next is null. No. I go to its parent. I check whether whether this component's next is null. No. I go to its parent, and here I see its next is null, basically. Okay. So there is one thing you should not understand that because this is a node that this has three children, its size actually is more than two. You should not believe that. Its size is actually the name and its next. So what is this pointer? This pointer is actually coming from the box here. This is not null. This is pointing to here, something here. Okay. So the root node will always have next is null. Okay. So through that I can check, except the of course the initial state, I can say that this is the root. When it is initial, this is the name itself. I mean, it is its own component. So effectively, how much time find operation takes? Find operation takes, actually it has to travel actually the height of this tree. Okay. So the biggest height that will be possible. So if this height is h, height of the tree, then one find operation actually requires the height of this tree. And one union operation takes one pointer change, that is essentially constant time, basically. And of course, make union find means I have to create this entire list. Creating one such box and making the next null, that overall takes constant time. I will do it in a for loop for all the vertices. So overall, this thing will require order of n time. But that is not too much a concern. Only concern is find and union. So here, union is constant, but find is actually order of the height of this tree. So if you look at the earlier implementation, union find was very fast. Find was constant, but union was linear, order of n. But here, the find is union is constant time, but find is actually order of height, right? So how do I enforce that this height is actually order of, if I can somehow enforce the height is of the order of log n, then somehow, I mean, my job is done. So how to enforce that? You see, there may be a bad case here. Suppose I have a tree like this is something. Yeah? I have a tree like this. Then this is a very, I mean, tree is a chain basically, and the height of this tree is actually never log n. Height of this tree is order of n. So this actually is a very problematic case. So in that case, height can be actually order of n. So that this kind of thing I should avoid as much as possible. So how to ensure that height is always of the order of log n? So this is done by this thing, that always keep the name of the bigger size. That means I change the name of the smaller size. So if you think of, if I change the name of the smaller size, what I will, so initially, what is the size of each component? Let's say each component is designated by CI. Okay, so initially CI is equal to 1. Right. Now, when I change the name of the component of the small, okay, so the smaller sized component points to a larger component. So that means I can claim that the size of this component this smaller component actually at least doubles. You can write the size of the component whose name changes at least doubles. Okay. See, suppose one component has some size, suppose delta. Okay. Another component's size is delta minus 1, suppose, or delta minus k, suppose. Okay. Then if I make this component parent, if I make this, then this component point to the root of this component, then I can say now overall component becomes a common name, and I can claim that this component, at least this component, at least doubles, at least doubles. But if I change the name of this component, then I can, everything becomes the name of the smaller component, but I cannot say that this component doubles. I cannot say that. But in this case, I can always say that the change this part at least doubles. Okay. So that's why by doing this, I can say that the size of each component under consideration whose name changes, that double at least. Okay. So what is the minimum size? That is 1. And what is the max size? Maximum of any CI that is possible, that is actually order of n, when all the vertices are there. Okay. So mean size is 1, max size is order of n, and in every iteration, or let's say I do not know how many iterations I need, every time the size at least doubles. Okay. So let's say I do not know how many iterations it does. So let's say I have, I have this, let's say x number of iterations. So I actually will do this. 2 to the power of x is of the order of, let's say, order of n, I can say. Then x is actually order of log n. So this conclusively shows that the height of this tree will never be more than log n if I follow this particular pattern of union, that always a bigger component keeps, or I change the name of the smaller component. Okay, if I follow that rule, then I can say this height will always be of the order of log n, and in that case, find will always be of the order of log n. Okay, so this linked list implementation says that union is constant, find is of the order of log n. It's just slight improvement. A little bit improvement conforming to our expectation. What is our expectation? Expectation is union and find both should be of the order of log n or less. So what we see in this linked list implementation, union is very easy, very simple, that is constant time. Find is actually order of log n. So both are actually conforming to the desired thing. Okay. But of course, you have to agree that this linked list based implementation of union find, this is actually a little bit more involved, more complicated. You have to take care of the pointers. So you should be careful about this. Okay. So, okay. For there are other kind of improvement of this thing possible. I mean, one can do even a better implementation of the union find, but let's not do it today. That is a small discussion. We will take up next class. So I'm stopping here. If anybody has any question, I have still 5 minutes are there. If anybody has any questions, So we can discuss.
Sir. Hello,
Yes,
sir.
yes.
Sir, is it possible that for any kind of problem we can create a find, I mean, union functionless, so that the smaller component is actually union with a bigger component? Is it possible in every kind of situation to create that condition?
Uh, See, union find data structure is mainly some sort of set membership problem, right? So basically, find means that I can quickly check whether. So actually, if you look at the Kruskal's algorithm, what you do when I give you two vertices, one an edge, you actually do this. Whether find u is equal to find v. When you are given an edge uv, you check whether this is true. If this is true, then you actually know that they belong to the same component. So one component is there, and this is my u, this is my v, so they belong to the same component. If I join them by an edge, there is a cycle. So now this kind of situation has to arise in a particular problem. Okay, if this situation arises, then I think we can do it. So
Okay, sir.
in, in some kind of problems, this may arise actually in some other set membership problems. So what I am interested in, I am finding the set membership of u and the set membership of v, and I want to quickly find out that they are quick. Okay.
Okay, sir. Thank you.
So I have forget this graph. Suppose I have two sets. Okay, one is, let's say, A, and that is B, and both A and B are actually, let's say, subset of a bigger universal set. Set can be anything: set of trees, set of numbers, set of rationals, anything, right? And now I want to quickly, I want to give you two elements, X and Y. Okay, and I want to ask whether find X equal to find Y. I want to quickly check that. So how quickly one can actually can linearly see through A, one can linearly see through B, okay? Or one can actually that linear, then both find etc. will take linear amount of time. It will not be quick, right? But here, if you do it like this, if you do a little bit of pre-processing, then you can make things happen in almost logarithmic time in this tree-based implementation. In array-based implementation, you can do it in constant time, but the union is there poor actually. I hope this answers
Yes, sir. Yes, sir.
your
Thank you.
question.
Yes, sir.
Excuse
Thank
me,
you.
sir. Sir, regarding tomorrow's quiz, we actually had another quiz scheduled from 4:15 to 6:15 p.m. So can you please shift the timings of the CS20 quiz to an earlier slot?
See, I have already made a 6 p.m. I already made this request long back. That time, why did I said 30th there will be a quiz, right, in the evening side. So why still that time you did not say?
Sir, the other quiz were actually announced at the start of the semester, like 5 or 6 January. So,
No, no, no. When I said that on 30th evening I will have a quiz, that time why you didn't protest? Why you are protesting now?
sorry, sir. Maybe I was not
No,
there
no.
in the
I
meeting.
I want to know how many people, any other person. I want to know it from any other another person.
So like maybe it's not uncommon for us to have multiple quizzes on the same day. So maybe we
No, no.
thought that the
I want to hear it from some more people. I just not from you. At this point, I will not change because when I announced this long back, only I mailed you. Okay, I announced it in the class long back. That time you did not protest. Somebody said, okay, 31st we cannot do. So I made it 30. Now you are saying again there is a change in exact timing. Why so?
So, but you didn't mention the exact time, and it's now conflicting with other quiz.
So like many a times it happens that we have even two or three quizzes on the same day. So sometimes, yes, the timings have to be altered a bit.
See, this is totally. I do not know how this is. Somebody is announcing a quiz from the first to go. Okay, this date, this time. That means I have to schedule all the quizzes of the month. If I say okay, every month end there will be a quiz. Can I do that? Arbitrary junks things.
Sorry, sir, we'll take care of it from the next time. For tomorrow, can you please just maybe even postpone the quiz by 20 minutes only, so the other
Okay,
quiz
that
will get
that
over at
that
6:15.
only I will do. I will do it. I will make it at 6:30. That's it.
Okay, thank you, sir. Thank you.
Mhm. Please do tell me when at the beginning. Okay, not like that. 1 week before I said that time you did not say anything that we have a quiz on 30th. Somebody says okay 30th first I cannot do. I make it 30. Okay, that day you do not say. Now just 1 day before you are saying that. That day you cannot say that. So 30 also I have a quiz. We have a quiz. That time you could have told. Actually, it is not. You are giving preference to some other course than this course. That is the main thing.
No, sir. Actually, the timings for that quiz were specifically announced 4:15 to 6:15 p.m. in the starting of the sem. But yeah, we should have mentioned this to you on the day you announced the quiz. So we'll take care of that from the next time. Sorry, sir, for the inconvenience this time.
Okay.
Mhm.
Okay. So we stop today. Anything else you can ask me or post me. Okay. So TAs, let us have 1 2 minute meeting, short meeting.
Excuse me, sir.